Welcome, and thanks a lot for the big audience that came tonight. So, as is sort of the yearly tradition within the Music Quantum Center, we have a very special night today where we have a very distinguished guest, Philip Kim from Harvard University, who will give a popular lecture on physics in flatlands. So welcome, Philip. Thanks a lot for being here. And before we go and I introduce Philip in more detail, so let me just maybe give you also a slow breakdown what is actually the Munich Quantum Center. So the Munich Quantum Center was founded in 2019, and it's the Munich Center for Quantum Science and Technology. And it's basically Bavaria-wide effort where we have the Ludwig Maximilians University here, we have the TU Munich, Max Planck of Quantum Optics, the Walter Meissner Institute, and the German museum, the Deutsches Museum, participating in this effort. And basically, the main effort, or the main goal of this cluster of excellence of MCQST is to discover and understand novel and unifying concepts in the interdisciplinary research field of quantum science and technology. And basically, the main goal is to make them tangible and practical and to develop a next generation quantum devices. So basically, what that means is that we are now in a second, or what is it, the third quantum revolution even, where really, whereas in the previous years, people have actually studied the fundamental aspects of quantum physics. Now, actually, the quantum physics became so well controlled that we can actually implement this physics knowledge into real technologies. And for example, we can start thinking of building a quantum computer or building the quantum internet, and I'll talk in a second a little bit more about it. So, okay, so who are the people behind MCQST? So those are basically more than 70 groups, again, distributed throughout these universities with more than 225 researchers. So I would probably say that 20 groups are actually at LMU, 20 groups are at TUM, then again, more at Max Planck and other universities. So it's really a very broad research collaboration between all those groups. And I have to say also MCQST was sort of the central platform for the general quantum community that has ever since developed in Bavaria and in Munich in particularly. So for example, maybe some of you heard that the Munich Quantum Valley was founded soon after. This is a 300 million euro project just in the Munich area alone, with the goal to build a practical quantum computer where also companies like, or research institutions like Fraunhofer are participating. So the breakdown of the research activities of the MCQST are the following. So they are really all core thematic areas that are remotely related to quantum science represented. So it's actually, if I compare it to other international quantum activities, it's one of the broader activities. So in particular, we also have a lot of fundamental research, such as, for example, astronomy and particle physicists that are actively participating in it. It spans all the areas from quantum information, quantum simulation, quantum computing, quantum materials, which in particular ties well to today's speaker. And maybe most interesting for you is that MCQST has also a lot of outreach and a lot of support structures. So for example, there are bachelor students, summer programs financed by and organized by MCQST. Master program in quantum science and technology exists between LMU and TU. There's a graduate school, there are junior research positions, there are seed fundings and so on that we created. And basically this is something which all of the students and the researchers in the Munich area can participate and apply to. For the more general public, there's also a lot of outreach activities where events like this are being created, where really world-famous scientists can come and talk about their research. There's public talks, open house days, science slams, and also what I think the community is very proud of, if there's a new Light and Matter exhibition in the Deutsches Museum, so you could, anytime, any day, you can go to the Deutsches Museum and there is basically a stand which demonstrates quantum technology. So I think this is one of those pictures actually shows the stand there. How to follow us? So I think there is again, how to stay on top of these possibilities and events. So please sign up for LinkedIn, YouTube, X, and what is this last one? That's new to me. There's also a website, MCQST. Okay, so this brings me now to the speaker today. So it's a very big honor to have Professor Philip Kim from Harvard University be here today. So Philip Kim is one of the leading scientists and one of the pioneers of the field of lower dimensional systems, and is basically one of the very first people to work on isolating graphene. Philip Kim also worked in a lot of other two-dimensional systems, such as carbon nanotubes, for example, and other two-dimensional semiconducting systems and many more. And Philip Kim's main sort of research direction is the electronic transport, quantum transport in these materials, optoelectronic properties, thermal properties, and I'm sure we'll hear a lot of these properties today. So just a little bit on the CV. So Philip Kim got a Bachelor's of Science and Master of Science from Seoul National University. After that, he moved to Harvard University to receive his PhD. Then he was a Miller Fellow at UC Berkeley as a postdoctoral researcher before moving to Columbia in around 2002, I think, where he became assistant professor. Basically, ever since 2014, Philip Kim moved to Harvard, where he's a full professor there. And basically, I think Philip Kim is one of the most highly decorated scientists that you can find. So, for example, Philip Kim got the Ho-Am Prize in South Korea in 2008. He got the Buckley Prize, which is of the American Physical Society, which is the highest prize in condensed matter physics that the American Physical Society gives. And last but not least, Philip Kim has also last year received the Benjamin Franklin Medal in Physics from the National Academy of Sciences in the US. So with this, Philip, thank you very much for joining us today. So I have also the pleasure to give you a little medal. That's the little medal that we, MCQST team has presented to you. So congratulations, and thank you very much for coming.
Thank you.
Okay.
All right. Wow. Was it real?
Okay, so.
All right. Okay. Thank you very much, Dima. I think it was a really nice introductions, and thank you for the invitations. This great town and this great occasion. It's my honor to be invited and also receive this award. I think that's kind of great. So as Professor Afetov said, I'm going to kind of share some of the interesting. Sorry, a bit too loud in my opinion. Some of the interesting aspect of the quantum materials, and especially the work that I have been doing, as well as the quite a big communities now actually has been doing to study about the quantum materials appearing in the low-dimensional system. I titled it that the physics in the flatland. Flatland, of course, is related with kind of two-dimensional materials. I'm going to kind of mention it, and we'll just guide you that how that is related with the quantum material research in general, and eventually how that can be useful for some technological application, especially quantum device applications. That's kind of the goal that I have. And on the way that you will see that this beautiful butterflies are hovering around these materials, and this is kind of part of the story also shared throughout this discussion. So let me start with this story about the flatland. In fact, the flatland is a title of the novel, which was written in the end of the 19th century, was done by the Edwin Albert's novel named as Flatland. This is kind of something like about 50 pages of the short novel, and it was kind of interesting read. It's about the stories about the square that live in the two-dimensional world, and that is a saga that kind of navigating this two-dimensional world, a lot of interest in the humors and the politics and so on. If you don't want to read this novel, in fact, actually, I found that there is a nice movies called the Flatland. It was now even available in the YouTube, so you can just kind of watch it, this kind of abridged version of the story. It's more or less faithfully the reflect the novels that are kind of written in there. It's quite kind of intriguing part. So the essential story here is once you get down to the two-dimensional limits, the world view is very different. As you can imagine that for us that live in the 3D and imagine the 4D, there are a lot of kind of the somewhat unusual behavior can be imagined that indeed kind of 4D. It is analogical that now is a 3D to the 2D. If you just can put yourself in the 2D limits and observe what happens in 3D, there can be quite unusual concepts that kind of arises. And that's kind of basically interesting story that many of us even just think about in childhood. Well, what if this 4D is existing, that what do we see the exciting part? All of these things, in a sense, that this low dimensionality, or 2D, 1D, 4D, and these are kind of our mathematical concept. And if you just ask that, can we realize that into real physical world? Obviously, that's not going to be easy because we live in the 3D, or if you just add up this one-time dimension, we live in the 4 dimensions, right? So all this kind of low dimension, 1 dimension, 2 dimension, it's all kind of mathematical concept. Why it becomes relevant in the physics and why it becomes relevant to the materials? I think that's kind of some interesting questions we can ask that about the materials in the low dimension. In fact, that's to understand that we need kind of the Stark evoked that kind of important concept arises from quantum mechanics. By the way, the next year is the World Year of the quantum mechanics or quantum physics in the worldwide. I think that's kind of related with probably about 100 years of the birth of the quantum mechanics, quantum physics, and how we can kind of counter 1925 is important. There's many ways that you can just kind of think about it. This famous photos of the conference, the photo, Solvay conference, where the founding fathers of the quantum mechanics kind of are sitting there. It was 1927. And this year is important, but probably 1 year before that is more important because that's where the Schrödinger wrote the famous Schrödinger equation, 1926, and probably conceived that his idea of Schrödinger equations or Heisenberg's the quantum matrix idea was born around 1925, and that's probably my guess is why the people think that 2025 is 100 years of the birthday. But the important part is already captured by this very first equations about quantum mechanics. Once you just kind of take the Schrödinger equation and ask what is a really essential part, the quantum mechanics is different from classical description. There are many essential parts, but something that you can think about when you just describe any simple object, such as hydrogen atom in quantum, the classical view, we know the electron is kind of circulating around the proton due to this Coulomb interaction between them. And naturally, the orbits is a kind of this circular orbits. And classical mechanics dictate us that this orbit can be arbitrary size and can take any energies, right? What quantum mechanics, once you apply the Schrödinger equations, kind of provide a very different world. Basically, solving the Schrödinger equations for the hydrogen atom, already you get this the wave functions out of it, but more essential part is you don't get this any continuous contribution of wave function, and wave functions and their corresponding energy is all discrete because of this the essential part of the quantum mechanics. So in a sense, that essential part that you can distinguish between classical world and quantum mechanical world is discreteness. Either description of wave function, also energy associated with it, and all this distribution, there's some sort of a discreteness is one thing that kind of very important, kind of distinction between classical world and quantum mechanics. And once you apply this concept into the many other systems, atoms and that very small object, as I mentioned, that energy scale is discrete. But if you just start kind of apply this a little bit more extended object, such as one-dimensional wire, extended these things, instead of your discrete energies, your levels becomes kind of the distribution is also kind of discrete type of the so-called band structures that describe that motion that in this one dimension can be also related with some of the discrete energy distribution. If you extend it into 2 dimension, you can get, again, discrete stepwise distribution of this quantum state. Again, extension of this kind of dimension. Of course, now if you go to the 3 dimension, becomes more of the smooth and continuous distribution is happening, right? So what you see here is that once you start kind of the decrease of one of the physics dimension, suddenly that this continuous distribution tend to discrete it and eventually step down to the really sharp distribution one can see in the atoms, right? All this object is a 3 dimension. However, once you confine this the one of the dimension characteristics such that quantum confinement ideas start applied, you usually get some discrete distributions of this quantum state. And here comes that interesting concepts of the low dimension that comes in. What if that my energy that I'm interested in, either temperature I'm working on, and strictly energy that I'm working on is a relatively low energies, such that I'm working on one of the discrete bands type of the structures. And that's where the motion of this the particle in confined space is effectively low dimensional, such that although this object wire and flat boxes a 3-dimensional object, effectively you can describe all these dynamics in the low dimension, and concept of the low dimensional system comes in. So in other words, once you get any 3-dimensional object and you just can shrink it down into a small scale, right? Typically atomic length scale or the nanometer length scale, which is about 10 or 100 atomic length scale, quantum mechanics dictated that the motion of the particle, especially electron that we are interested in today, is it can be described by this low-dimensional physics, such as effectively 2D and effectively 1D. Atoms, you can think about effectively 0D system in that regard. And therefore, that the low dimensionality comes in this sense, right? This sounds like the esoteric idea. However, now this becomes quite important, kind of technologically. We know that nowadays we are using all the telephone and computers. There's basically the computer chip is dictating modern electronics. Modern electronics has been developed over the past probably half centuries in such a level that if you just kind of open up these computer chips and look at the inside, there's a kind of rather complicated kind of semiconducting structures out there, right? And this dimension of the semiconducting structures, especially its core, which is still kind of semiconducting transistors in there. If you just kind of zoom in this core of the transistors and look at this kind of high-resolution electron microscope, now it's about the tens of nanometer, right? It's about 100 atomic length scale. But the real core of the transistor there, if you just zoom in, actually the silicons, that gate dielectric and the metal gates on the top of that, this gate dielectric thickness is approaching to the sum of the few nanometer, only 10 or 20 atomic length scale, where that now such a kind of quantum confinement becomes quite important, right? So basically in our pockets, all the electronics, basically quantum mechanics start kind of dictate their kind of behavior in some sense. And that's kind of interesting argument one can make. Not only this type of this modern electronics in our cell phones, in fact, the scientists and the engineers has been developing the way that one can really control the materials in down to atomic length scale, that almost kind of one by one, and create at least kind of this two-dimensional system. Starting from the 1970s, almost kind of 50 years, that there's engineers and scientists that developed a technique called the molecular beam epitaxy. And this is nothing but just a vacuum chamber with a kind of well-controlled evaporators that evaporated the various materials, including the semiconductor, onto the substrate. And they can create this wafer scale of the stacks of the semiconductor. If you just cut out this semiconductor, you can often see that, again, this high-resolution electron microscope, you can see that this kind of stacks of the layer. All of these layers are made of the carefully designed the atomic layers of the semiconductor. Somewhat different kind of the properties. Often this is what we call the semiconductor heterostructures. And in principle, you can control all this kind of different atomic layer. And you can imagine that any electrons and even phonons that the moving around these layers is extremely confined to 2 dimensions, and therefore you can realize some of the interesting quantum mechanical properties out of it. Indeed, this type of heterostructure has been used as a kind of important in modern technologies, and high quality of the transistor or the optoelectronic devices is actually rely on these heterostructures, not to mention about a lot of interesting physics arising from this one. I'm going to briefly talk about a little bit later. Interesting part is it's only kind of starting point. There are yet, about 20 years ago, the different type of the way that you can create the extremely confined 2-dimensional electron system, often called the graphene. Graphene has been known for hypothetically for the many people that work on the graphite, because the graphite and some of the materials are layered structures, and single atomic layer of the graphite is what is called the graphene. But it was until that about 20 years ago that the duo, Andre Geim and the Kosten Novoselov, first demonstrate this graphene can be extracted and can exist, and that provide us a kind of exciting properties out of it. And from there, the contribution only takes kind of 6 years. They get the Nobel Prize in 2010 by just kind of this amazing discovery of this material of the graphene, which is one of the first kind of the 2-dimensional system that comes out rather different way. Anyone that know that how they get this the graphene first, by the way? And many people just work on the 2-dimensional system, and they're using the Scotch tape, right? So I was one of the researchers that back then working on that, tried to find the graphene with somewhat different way. But I was really shocked just reading their paper, how they get these graphenes out. And indeed, it was literally using Scotch tape. Interesting enough, and this technique is still being used in the modern labs. After 20 years in my lab, you will find a lot of Scotch tape. If you are not believing me, visit the Professor Efetov's lab, and I see that his lab, still the students use the Scotch tape, just getting this one. So it is still the way that you can get the extremely high quality 2-dimensional system. In fact, if you are interested, and those of you who don't know, this can be done in your kitchen. And usually in United States, often that this is, do you do yourself, right, in your kitchen. If you have the graphite crystals, and if you can buy that, put onto the graphite flake onto the Scotch tape, and just put this Scotch tape on the kind of flat surface like the silicon wafer, and rub it behind of that, and just kind of peel off the Scotch tape. And then if you just look at the carefully the flat surface, you will see that, of course, some kind of the disgusting Scotch tape glues there. But if you just kind of look at it very carefully, using kind of decent optical microscope, you can actually find out very faint kind of this color, the graphite crystals. And in fact, the faintest color, the graphite crystal, is correspond to one single atomic layer of the graphene. And that was basically the starting point of this studying about this 2-dimensional system, 2-dimensional materials, slightly different way. Compared with MB, typically costs about millions of dollars. This one takes only kind of few bucks to can create this kind of quality of sample, and you can still kind of get interesting physics out of it. Of course, this was a beginning, but over the time that there has been other method and other way that you can create the other type of 2-dimensional system. So over the past 20 years, the community has been developed. So not only graphene, you can get a lot of different type of the 2-dimensional material, as long as the nature provides us this layered materials, often the Van der Waals system. You can use very similar technique. You can extract a single atomic layer, but moreover, not only you just extract them together, extract them onto the surface, you can pick them up, you can restack them to create some of this type of heterostructures. And as you can imagine, that if you have the different type of the 2-dimensional materials, their property can be different. So once you assemble them, you can get this nice, interesting properties out of this type of the stack. And that has been one of the important topics in past probably 20 years, so-called just using this 2-dimensional system to make this stack into the kind of some of the interesting device form. So this is not only just nice cartoon that we can draw here. I think I can give you some few example here. That, for example, here that it was a graphene and boron nitride. By the way, boron nitride is graphene-like the structures, but it was consist of the boron and nitrogen. Turns out it becomes kind of nice insulating materials. And down here that we color, this is a 3-moly disulfide layer, and this is a so-called the transition metal dichalcogenide that comes as the semiconductor. And you can see that those kind of things can make the stacks. And the way that we can make the stack is cleave this crystal and pick them up. Or nowadays, some people actually even grow these materials series by in the serial way to make these heterostructures. But nevertheless, the whole point is, like the MB grown sample, you can make those kind of heterostructures and try to look at the interesting properties out of it. This can be kind of readily done in many labs. And here in the Munich, that of course, Professor Efetov's group actually is a real expert at creating this type of structures, as well as other groups as well. Here's another example. Here's the structures made of, I think this is a high temperature superconductor bismuth strontium calcium copper oxide. Name is long, but again, the idea is basically you can make those kind of stacks, again, by cleaving these crystals and restack them together. So I can just demonstrate that we can make this type of interesting crystals and different structures out of it. What is it useful? I think that's the next things. So I can see that, you may see that now, you can get very thin atomic layer, you stack them and make the dysfunctional structures. Can we see something useful or something interesting out of it? So that's basically next story I want to tell you, right? So that's the story that I'm going to kind of share together. It's again dated back to the quantum mechanics and especially quantum applications based on quantum mechanics. Then we can say that what other interesting I'm also already mentioned about the discreteness is one of the important part of the quantum physics. What other interesting property we can mention and that can be useful or important for the quantum application? Probably two concepts that kind of comes around is so-called this quantum superposition. And this is kind of rather unusual concept that you can have the two distinctly different quantum states. But in some sense, in quantum mechanics allows us to superpose this kind of two states as a one quantum state. And famous example is Schrödinger's cat, where it can be half live and half die, right? And can coexist until you observe this one. Even more exciting concept is you can make these superpositions and not in the locally, and this cat, you can just kind of make this superposition locally, but you can actually separate them as long as that you have the coherence can be maintained. And this is a concept of the entanglement, and non-local superpositions can be possible. And then that one state onto the farther away can be deeply related to another quantum state in the other location. And all of these things can be very essential topics that one can use for some quantum application. Of course, there are many applications there, and the important quantum application is basically using this type of the superposition entanglement as a quantum information processing. And there, the classical bit, usually coming down 1 and 0, can be replaced by the, and that build up this classical logic, can be replaced by the quantum bits, which actually is again 0 and 1 states, but that unlike the classical bit, is only 0 and 1, either one of them. Quantum mechanics allows us that we can, in fact, that superpose this type of state and create interesting enough, although we start with a discrete state, we can make the continuous descriptions out of it. More exciting part is you can also entangle these multiple quantum bits and just kind of separate these things out, and you can make this kind of non-local type of this the properties out of it, and that will immediately allows us very different type of the quantum logics. And one can just kind of outbid this kind of the classical, the logical operation. Hence that the quantum, the computing is one of the important topics that potentially outrun the classical, the computing that we all kind of enjoyed up to now. So this concept of this, the quantum computing or quantum information processing has been really strong, the field in past probably about again the half centuries or so. Professor Efetov mentioned about this, the second quantum revolution or third quantum revolutions. Probably second is probably properly people called. What is the difference? I think first quantum revolutions comes from 1926 or 1925, where the quantum mechanics really sets in. Second quantum revolution is probably related with that now that engineers as well as physicists start to obtain say controllability of the quantum system such that we can just realize those kind of the superpositions in entanglement in certain material platform or device platform that we can start to kind of utilize those information processing process. So there, of course, we need some sort of platform to realize this. And indeed, at this point, we don't know what is a winning platform, but there are many different platforms. There are at least several promising platforms has been suggested in the communities, and that it can be using superconductor, quantum dot, color sensor, trapped ions, and then more importantly, I just can miss it out. But of course, here that the neutral atom, readable atom becomes kind of another important platform recently comes out, really kind of promising, right? So these are something that in past 20 years that people start to realize and refine that and getting to the level that now you start to get this kind of few quantum bits, or at least kind of even tens of hundreds of quantum bits, qubit is possible to realize it. It's not only scientific endeavor, then many big companies, including the startup as a big IT company, start kind of invest a lot onto some of this platform, indicating that indeed this becomes not only scientific endeavor, but really material, or that industrial, that endeavor starts comes around. Of course, I cannot go over all of these things, but good example that I can just kind of show is superconducting qubits, where simply you make some small superconducting circuit. It's kind of Josephson junctions or the squid type of the junctions that you can create it, which give it the controllability. More important part is because of this superconductor, supercurrent can flow through this ring without dissipations, without damping. And it depends on the direction of the supercurrent. You can make this the qubit up and down. You can create those kind of two states. You carefully just control this type of the superconducting ring. For example, you can build up these qubits, and you can just kind of build up the many of them. You can just kind of easily create these circuits, or that the quantum circuits build up the many of the qubits that can realize some quantum the algorithm into this type of the system. So that has been kind of really one of the breakthrough happens in past 10 years or so. Many of you just kind of when you find out quantum computers, and this is kind of often the figures you will get, and this is nothing but, it's not a real quantum computer per se, this is basically a dilution refrigerator which cool down this quantum chip down to the low enough temperature such that you can maintain this quantum coherence into the this superconducting rings or superconducting circuits to realize this quantum computer. But nevertheless, you haven't heard about, you have probably heard about the stories about the quantum computing based on this superconducting qubits. All of this, the superconducting qubit per se is built onto the some superconductor, which is made of the aluminums or niobium and those kind of rather conventional metal that build up in the small scale to make these circuits. And it has been quite promising. However, there is some of the issues here, and that's basically where my story started out. The issue here is that when you just build up the quantum computer, of course, you need the qubits, and number of the qubits will tell you about this strength of that capacity of this quantum computing. It turns out, even if you make this superconducting qubits out of superconductor, all of these superconducting qubits are a bit different from each other. And moreover, there is some variation of environment. There is a noise and various things. Try to kind of decohere these superconducting qubits. So one of the important parts to do the quantum computing is maintaining the entanglement and for long enough time just to do this the computation. And this decoherence is a real issue. And the way that you can prevent, or the way that you can cope with this decoherence, is making basically many qubits connected together and connected this so-called physical qubits together to just kind of compensate those kind of error appears, and this is quantum error corrections, to make the one logical qubits, which actually considered as effectively not decohere. It will take the kind of many physical qubit, depends on these properties, to make the one, the logical qubits. Which means that if you make the kind of 50 qubits working in your circuits, turns out in the background, you need probably something like the several hundred or thousands of the qubits needed to doing that. So you can quickly see that we can quickly bump into these issues of the scaling up our the qubits, or qubit arrays for the real quantum computing. Unless there is a way that you can suppress those kind of error containing, basically we have to deal with basically many qubits needed to make this kind of working qubits. And there comes basically this idea of the quantum materials, especially topological protections comes in. So it's been about, again, 20 years. People have been they propose that if somehow your hardware that you build up the materials, that certain quantum material has a special topological properties such that it basically prevents the coherence by just kind of entangling those kind of quantum information inherently non-locally, and often that this is related with topological the concept. Maybe those kind of the materials that if you build up the qubit out of that material, you can just kind of make these qubits the vigilant onto the coherence. So that was the idea, and there are some of the proposals that how we can construct this kind of topological qubits out of it. Now, to explain this topologically protection and topological qubit, maybe it's probably a good idea to step back and ask what is the meaning of the topologies, right? Remember that I started out this talk to just kind of convey you that, the low dimensionality or dimension comes from the mathematical concept, right? Lines and the plane is a strictly the mathematical concept. Any physical object, to get there, I need kind of quantum mechanics to kind of make the effectively low-dimensional system. What is the meaning of the topologies here? To do that, we can start with the kind of how the mathematician define the topologies. So if you go to the Wikipedia page, for example, and ask what is topologies, and the topology is basically a branch of the mathematics that allow you to categorize some of these shapes of the object in some different category. And it's where you actually rely on the interesting the properties. Here that detailed shapes and detailed geometry doesn't matter. It's more important that whether you can continuously deform one of the shape and map into the another one. And the good example you will here see that it was actually direct copy from Wikipedia pages. This mug cup is the same as donuts. In a sense, if this donuts is made of the clay, I can deform this donuts to make the mug cup and vice versa. And here that I just don't have to punch the new holes or this detach some of the things and this continuous deformation. Therefore, that you can just map this as kind of same topologies. And in topological way, there's one holes into this three-dimensional object, right? Turns out that topologies, that if you go through there are many interesting objects that the mathematicians study about the topologies. And often that topological unique system is something like this trefoil knot is a good example. This is a knot that you cannot just undo without this cutting up, right? That's kind of a good example. Many of you probably play around with Mobius strips somewhere when you're a child, right? So this is another good example. You can make these strings, but instead of make the band, if you twist it and connect it, and this is these strips that basically there's no outside and inside. In other words, basically you're starting from the outside. One take the turn that you ends up with the inside, and take the two turn you're going back to the outside. We see that this is kind of rather unusual topological properties. Often the mathematicians just kind of classify with the kind of rigorous languages, right? Again, this sounds like the kind of rather interesting mathematical properties. How this can be related with some of the physical objects that we are talking about. So that is my next things. To do that, we have to step back into the physics and kind of show that really good example demonstrating the topologies. We have to go back about 150 years ago, right? It was about the time that Eddie Abbott wrote this the Flatland novels. In terms of the physicist, the name of the physicist I'm going to bring it up is Edwin Hall. In the end of the 9th centuries, Edwin Hall was testing that interesting idea that back then was a kind of new ideas about this Maxwell's that electromagnetisms that kind of just synthesized. And there's an important kind of concept of when charged particle is moving in the magnetic field, there's a Lorentz force to bend these particles around. So what Hall wants was kind of measure those kind of bending of this charged particle. And the way that he just designed the experiment is if you have the very thin the metal, such as the aluminum foil, and sending the current through the one direction, and subject under the strong magnetic field, and then any charged particle, back then considered as electrons or whatever charged particle that moves around, bend around, and kind of developed the voltage across the sample, and simply measuring this voltage, when you just kind of send the current under the magnetic field, you will get those kind of amount of this bending due to the Lorentz force, work it out. So that was a simple concept. Experiment was, by the way, the hard. Before Hall, that several people tried out, didn't work it too well, because this essential part that work it out is how to make the really, really thin materials is a kind of essential part. And the reason that Hall chose I think it was called the gold leaf back then, was clear, right? Because already in the mid-over area, the human knows how to make the gold really, really thin to make the various things, right? Gold kind of the plates and those kind of things. So gold flake with about the less than micron thickness of this film is a really essential part that back then state-of-the-art way that you can make the really thin materials, right? With this, basically he saw that indeed, due to the Lorentz force, when you just increase the magnetic field where that increase the Lorentz force and measuring the Hall resistance, which is nothing but voltage you read across the current direction divided by the current, is basically linearly changing with the magnetic field. And giving that, all right, Lorentz force becomes stronger and stronger linearly with the magnetic field, and that's kind of what he found, right? And that was kind of quite important discovery back then. And of course, this slope is a very important quantity. Basically, this slope tells you that how many charge carriers you have in this the whole film. So ever since the Hall discovered this Hall effect, it becomes one of the important, not only demonstration of this the Lorentz force, but later on that when semiconductor comes around, this is an important way you can measure the carrier density, the charge carrier density inside of your sample. So it was 150 years ago. After 100 years after this discovery, almost exactly 100 years after, there's yet another important discovery that happens here in Germany. The famous Professor Klaus von Klitzing in 1980 found very interesting properties. Now you can imagine that 1980s, that's the time that people start kind of make these semiconducting device in the integrate chips and kind of getting into small. Especially that's the time people start to make the heterostructures out of it, or the silicon MOSFET out of it, right? And that's a way that you can start kind of confine the electron really at the surface or interface of the semiconductor. And that's a time that now readily available, the strong magnetic field created by the superconducting magnetic coil. So you can imagine that that's about the time that you can start to see the real quantum effects of this Hall effect. So what do you expect to see that is if the electron is really confined that into the interface of the semiconductor, you just measure this one, you get the control this density, you may have the linear curve where the slope is changing by just kind of changing the number of the carriers in here, right? But quite surprisingly, and quite unexpectedly also, that what the Klitzing found was not a continuous change of the resistance, but there's actually steps that appears, right? And that was quite surprising. First of all, that why this kind of discreteness comes in, right? And initially, that kind of people just kind of wonder why this kind of this discrete step. But if you start to think about, already I gave you several keywords, right? Because this is now really confined, getting to the really 2D limits, very strong magnetic field, and drive these things to real quantum limits, right? And without even any calculation, you start to immediately think that, oh no, quantum mechanics plays a really important role because it comes as a discreteness, right? In fact, to understand this one, by the way, so this one basically within 5 years, because this is important discovery, he got the Nobel Prize, right? Understanding this type of physics actually dated back already. Lev Landau, that very famous Russian physicist in the beginning of the 20th centuries, just after a few years that Schrödinger's equation, he solved that how the electron in the 2 dimension, as well as the 3 dimensions, move under the constant magnetic field. And there comes a very important concept of the Landau levels and quantization of the cyclone orbit. The idea is rather simple. Basically, under the strong magnetic field, that this particle will just make the circular orbits, right? Simply applying the quantum mechanics, this orbit should be quantized, right? But if you just think about, I mentioned that, the quantum mechanics solving the Schrödinger equations, one important part is we get the so-called wave function that satisfies Schrödinger equation. In fact, the Schrödinger equation is equations that contains all the complex number. So not surprisingly, the wave function we are dealing with a complex number. And then if you just think about how to write the complex wave function has its magnitude, and also it's called the kind of the numbers called the phase. In other words, angle is important, right? And we know that our angle from the 0 to 360 degrees, it come back to the 0 again, right? So this often we call the periodic boundary condition is important. And that's kind of what dictated this quantization and make this orbit is rather discrete, right? So that's kind of one part. But the important part here is especially in getting to 2 dimension, this angle is only one angle, kind of in the 2 dimension, has a special meaning because it's a periodic boundary condition. 0 is the same as a 360 degree, right? Any angle, arbitrary angle, carries one important discrete numbers there. Anyone know? Anyone guess what it is? If you go to the, say, 0 to 360 degree, I just rotate more. Say I get this 160 plus 180 is what? 480, right? 480 degree is the same as 180 degree I mentioned, right? But that's basically 1 ton plus 180 degree, right? So as I just kind of rotating more and more, I have kind of number of the ton is basically integer number, right? That's because everything is contained in the 2 dimension. If I just rotate it around, unless I just kind of tear off this line and reconnect it, basically number of the ton cannot be changed. So this is precisely what mathematicians say, that those kind of angle, phase angle in the 2 dimension carries one topological number, which is a related ton. Winding number is kind of what they are saying, right? Why that is important? Think about these lines there, right? You can quickly see there's kind of interesting things. The first line, by the way, it was kind of so-called this is glitching numbers, is related with kind of, let me call this is the first step. It turns out the second step is half of the first step. The next step is 1/3 of the first step. And what you can guess what is next? 1/4, 1/5, right? So you can see that there's integer numbers is hidden in this step, right? And that's once you solve the quantum mechanics problems, right, onto these cases, as Landau did, it's precisely related with this wave function phase is whether it's winding once and twice and 3 times, right? So it's not surprising that this step is well defined because the winding number is only the integer, and that's basically quantum mechanics dictate onto this one. What you see here is a good example that how the topology comes in, right? I think this is by simply getting to 2 dimension and applying this strong magnetic field, we get the topology out of it. And why this is interesting? Because of this. This is so robust, right? Quantum Hall sample that once you grow this 2-dimensional system, you carve it out by just tweezers, make this type of this sample, and you just kind of glue it down with the lead solders. It looks so ugly samples like this, right? But you put this sample in the magnetic field and measure the Hall effect, you will see that this precise quantization, right? In some sense, it's so ugly, but nevertheless, I think because of this topological protection, this step is extremely well defined, and that's kind of important part. And you already start to see that strength of this topological protections there, right? That's kind of related, yeah. So that's in fact related with the topologies, right? Furthermore, I think there's a kind of interesting part. There is a kind of semi-classical way that we can describe this quantum Hall effect. As I mentioned, that this is quantized orbits we describe, right? And most of the sample that we are dealing with is not infinite sample, it's finite, right? And you can just draw that, all right, there's a quantized orbit I mentioned, but quantized orbit means that basically electron is kind of circulating around. You can quickly see that when we send the current through this type of system, if the orbit is quantized, the orbits inside of this sample cannot carry the current because they are just kind of circulating around, right? But then how the current can flow in the sample? The current is actually flowing because of this orbit at the edges. It basically cannot make the kind of full circle. Then they will bounce off. And throughout this bouncing off motion, the current can flow through the edges, right? This is cartoonistic pictures, but mathematicians in fact prove that if there's some topological protections there or topological unique systems such as that what I just described, the finite winding number, when this sample is ending with some of the other type of sample, in this case the vacuum out there, always the topology dictated in the middle of the sample is related with the edges of the sample, and often this is the bulk and boundary correspondence. In some sense, that this topologies that we just described, finite winding number, or physicists often call the Chern number, is related with those kind of presence of the edge state. And note that this edge state is one side going up, one side is going down. It's complete separate directions, right? Therefore, the current that flowing in here cannot just kind of easily scatter off the current from there, and that current can flow here almost kind of dissipationless. So it was a weird sample. Under the magnetic field, somehow this sample, basically when you send the current through there, there is not much of dissipation, or actually no dissipation in ideal condition, right? So energy can flow without dissipation. Almost kind of feels like the superconductor, but it's different from superconductor, but nevertheless, similar idea worked it out, right? Why this can be useful? This is related with the following idea, right? So if you just think about the markets with the kind of full of the cars and the people's around, right? Usually that doesn't happen in the German, I guess, yeah. Or maybe if it happens in Munich, right? Basically, either peoples and cars, the traffic is really slow because everything's kind of scattered off from each other, right? We know that how these things work in a really efficient way because we just separated that kind of directions. People moves in different directions, car moves in different directions. Basically, if you just kind of separate it out, the direction of move, right? This is basically the way that you can make the cars move really, or people move in a really efficient way. And that's precisely what we can see, that those kind of chiral state I mentioned in the quantum state, the informations as well as the energy can efficiently flow in the system in opposite directions, right? You may say that, okay, that sounds okay, but this is really practical. Are you saying that to work on this type of the edge mode and transport mode, should I just kind of bring that under the very strong magnetic field? Well, is there a way that we can just get these things without magnetic field even? That's kind of next stories. In fact, the next story, we need kind of another kind of interesting physics, which is related with spin. So electron has its interesting property called the spin, right? And you can view that electron as a ball, and electron is charged object moving around, circulating current, there's a magnetic moment comes around, and this magnetic moment is a three-dimensional vector, so you can just kind of point in any direction, right? If you just kind of want to describe three-dimensional vector, how many components we need? 3, right? However, turns out the electron spin in quantum mechanics has a very peculiar properties. Although it can point out any directions that for the electron spin, often the physicist jargon as spin half object, only 2 components to describe this spin direction. Even if it is left or right, using the 2 up and down of the spin direction is enough that I can describe the spin direction. That's kind of rather peculiar property of the electron spin. When you learn about the quantum mechanics, basically this is the first non-trivial example that we see. The quantum mechanics is really different. Because of this 2-componentness, there's another interesting peculiar properties of the electron spin comes around. That's a kind of following statement. If I'm holding the electron, if I have an electron, if I just kind of turn around 360 degrees, you see that kind of I didn't change it at all. But if I hold the electron, you will see the wave function describe electron. Once around the 360 degrees, it changes. Almost it's there, but with a negative sign, which means if you turn around twice, 720 degrees, it's only when that happens you come back it's your own, right? That's kind of weird properties. This is as if something like the Mobius strip, right? If you're just starting from the Mobius strip, you just turn around 360 degrees, you got the opposite direction. So only you just turn around 720 degrees, it's come back its own sign. So you already start to see that this is one peculiar properties that innated with the topology of the electron. More precisely, spin half particle, any spin half particle contains this kind of interesting topological properties there. Right. This is relevant for anything that I discussed over quantum O? Yes, indeed. It's related in the following way. If you look at the graphene lattice, quickly you see that it's hexagonal structures, but if you just look at the carbon atoms consist of the hexagonal lattice, there are 2 carbon atoms you can see, right? One I just kind of label blue and the other one is red, and they see that their chemical bond is opposite directions, right? Kind of directionalities. So you can see that any electron that's sitting onto this graphene layer, to describe this electron, I need, in fact, 2 components. One related with the red carbon atoms, and the other related blue carbon atoms, right? 2 components, right? This 2 components is exactly mathematically mapped into the 2 components of the spin up and down. And hence, once you just kind of describe the electron properties, electron contains this, the 2 components is related with spin like the object, often people call the pseudo spin, is innate here. What does that mean is, when you look at the quantum Hall effect, that seeing this is the graphene, where the electron in the graphene is responsible for this quantum Hall effect, you can see that the sequence is somewhat different, right? This is the first step, and second step is not in half, right? Third step is not in half. In fact, if you just look at there, the step goes something like 1, 1/2, 6, and 10. So integer number 2, 6, 10 is kind of important. What is next number? 2, 6, 10. Next one is 14. And if you just generalize that, basically we can write down in this way. 4 is less important for now, but what is important part is this half integer, right? What is this half integer? Where this half integer comes from? This is precisely that related with electron is take the 1 tons there. I told you the first step is 1 ton, second step is 2 ton, right? But this 1 ton is not for the graphene electron in the graphene is not full 1 ton, but that's basically half ton because of this pseudo spin I was talking about, right? So that explains basically why half integer comes around, right? So this is a good example that if you just engineer the electronic structure, such as kind of graphene, there's a possibility you can just kind of innate it, the topologies into the electronic band structures there. In fact, this is the already discussed in kind of the older languages of the Dowles and Haldane, who get this Nobel Prize for 2016 out of their seminal work on the topological electronic structures. They actually came up with a way that kind of describe those kind of structures related to kind of this physics. And that's kind of another interesting part. In fact, starting from here, that field start kind of moves really fast. So there has been kind of series of these materials in past 10 years discovered that basically putting these topologies in there, you engineer some of the topologies, you can get those kind of the edge states related with the non-trivial topology can appear even without the magnetic field. And that's not only theoretical proposals, but one by one, experimentalists also found those kind of real systems to realize this kind of innate topology into the system. And that has been something that related with this, some of the two-dimensional system, just put the topologies into this, this type of structures to get this, the topological systems out of it. So I have the kind of for a few more minutes, but I want kind of to touch upon that yet another kind of third aspect where this, the Van der Waals, the layered material is kind of interesting. And that is related with not only just kind of stacking many different materials together form the heterostructures, but stacking even the same materials. And that comes with kind of this kind of interesting cartoon. So let's think about this as a relatively large scale of the graphene sample, but imagine that I just put another sample on the top. But instead of this kind of on top of each other exactly, but some of the twist angle between them. So people, you can see that there is some sort of interesting complicated patterns comes around, but there is some kind of larger length scale of the periodicity comes in, or quasi-periodicity comes in, and this is what we often call the Moira pattern. And often, this is when there's two different, two similar systems kind of coming together, this is what you often get this kind of interesting, the patterns out of it. Why this is interesting, why this can be also important in terms of topologies. And for that, I can just kind of remind you some interesting children's case of toy. You can kind of see often that the toy is something like this. It's what I call the spirograph. and there are different number of the teeth in the system. When you just put the pencils in there, just kind of draw things, you can get kind of interesting drawings out of it, right? And this is a way that you can get kind of rather complicated drawings in the periodic fashions, right? This becomes periodic because these two diameters, or that the number of the teeth is only integer numbers. So if you just kind of think about two integer ratio, as long as you get this kind of greatest common multiplier type of the term, you will get this kind of the periodic fashions. But momentarily, you can think about, what if that now this ratio is not a rational number, but if it is an irrational number? What do you expect to see? Well, the complicated pattern will never come back. There is no periodicities, right? So that's kind of interesting part. Can you actually think about that? In fact, there was a person who thought about this one for some time. And that's actually this person, Douglas Hofstadter. If you're a non-physicist, and if you just look at this name, you're and old enough, then he wrote a kind of really interesting book called this Gödel, Escher, and Bach, that in the 1979. And this book was one of the famous books that got the Pulitzer Prize back then. Has actually interesting ideas in there. In fact, he kind of wrote this book and then basically weaving through the three different important ideas. One is Gödel's incompleteness theorem, which actually tells you that there's always incompleteness, that when you just consider some axiomatic formalism, there must be always some sort of loop and holes you cannot just kind of completely prove. And then he just kind of contained a painting of the Escher and music of the Bach, right? And especially Escher's figures, often you see that, something like this, right? It's a kind of enigmatic figures always drawn, right? Especially he chose Bach music, something like this, right? This is endless rising canon, where if you just hear this music long enough, every time you got just kind of go to the next thing, it repeat the same theme, but one major up, right? So after that 7 times repeating, it got a kind of 1 octave up, right? And this two thing is basically emphasizing that there's an interesting loop that can be made, right? And this is kind of open loop, it kind of never ended. It's basically tied it back with Gödel's ideas there, right? One thing less known for non-physicists is Hofstadter is known for also kind of physicist, wrote kind of very important paper, by the way. And then in that book, in his book, by the way, he mentioned about so-called this G-plot, and in that book, without any kind of context, he just kind of put the G-plot, and this is basically you can see that, well, look like the butterfly, but there's a kind of similar properties there. If we show this type of pictures to the mathematician, they will recognize that this is fractal-like structures, right? Self-similar and going through, right? But why actually he showed this one in his book? Because he was a physicist. He got the PhD just before he wrote this book, and his kind of important contribution, in fact, was published in the physics journal, right? And by kind of the idea is, well, you know, that once you have some periodic structures, 2 different periodic structures, and how that is related, energy spectrums and quantum mechanically, you have to solve so-called this hypothesis equation. In 1970s, using the personal computer available back then, he showed that solving this the equation numerically, you can get this energy spectrum out of it. And this energy spectrum is a very first example of the quantum fractal that exists. In fact, actually, this word, the fractal was invented after his paper. So he just used a G-plot, that's just a pretty generic name, but just can plot out this one. Why this is kind of related? Basically, one system you can make this one already. Hofstadter, the proposed there is applying the magnetic field in constant the periodic lattice, where you have the electron band forms by periodic lattice structures. Applying the magnetic field will give you yet different type of the periodicity. And when those kind of 2 periodicities doesn't matches up, you will get this fractal-like structures, right? Ever since in this paper, many people tried out to create those kind of structures or those kind of things realized in experiments. It only comes in around kind of 10 years ago that few different groups, including my group, realized that those kind of things can be realized by just putting these two systems together. For example, graphene sitting on top of the boron nitride, where boron nitride is very close to graphene. So not surprisingly, as you can imagine, the water can form pattern forms because these two lattices is very similar. And that water periodicity will give you the period, one periodicity that compete with this periodicity that given by the magnetic field in the lab scale. And using this one can show that you can see the quantum artifact, but sequence is not just a regular sequence. It is more like the kind of the randomized sequence or chaotic sequence that's precisely related with this fractal energy landscape in the system. And that is one good example. Indeed, this type of the engineering that what can make the model does something the electronic structures and start kind of modify their topologies there. In fact, this type of the things is actually carrying over quite a bit. And one important breakthrough happens in 5 years ago when the Pablo Harrio group in the MIT, just not using graphene on top of the boron nitride, but simply graphene on graphene, and where then now interaction between the electron in the water becomes important. What they just showed is once you just kind of stack the graphene in the right angle, right twist angle, so-called the magic angle, they see that graphene becomes a superconductor, which is kind of completely unexpected, right? And turns out the understanding this kind of superconductivity in this one kind of related with the topologies appearing in this system as well as the interaction in the system ever since it becomes kind of quite important topics, right? It was not only just seeing that microscopic-wise, you can see that indeed those kind of water plays kind of quite important role. It's not only the graphene, now they actually people pushing into the more of these other layers, and this becomes one of the really exciting field that's kind of pushing around to realize topology in the system. And hence, basically, this is kind of related, right? And I just kind of told you that indeed this quantum materials or engineering quantum materials, you start kind of engineer the electronic properties, including the topological structures in there. Now, I have not yet closed down that the connection, how this topology is indeed coming to the real device form, right? Well, so that is yet another topic. I just don't have enough time because already I overtimed a little bit, right? So I will just defer this interesting idea, how the topologies and superconductivities and all these things in kind of creating these things for anyone got interested in my next talk, in the Wednesday especially, more of the general colloquiums, at least the physicists can understand. Non-physics friend, probably you ask your physics friend what it's about, and that's kind of how I'm going to kind of summarize a little bit of the connection, how we can make those kind of quantum material platform into the just kind of protected, topologically protected this qubit operation. It's a yet kind of really developing stories. We are still kind of quite far away, but community start to make kind of really meaningful step progress in here. It's actually quite exciting stories. All right, with that, let me just kind of close out with the last comments. By the way, Flatland 1 was kind of rather successful, so they decided to make the Flatland 2, and subject there is interesting now, right? So this is a two-dimensional guy, not only traveled to the three-dimension, but now he ventured to the four-dimension, and stories about how that four-dimension is wonderful. And there, basically, even the wonder for the people living in the three-dimension will start to see. I think this is an interesting topic you can see. Okay, with that, thank you very much for your attention.
Okay, I speak in here, right? Okay, all right.
Wow,
so,
that's
okay,
interesting.
thanks very much, Philip, for the great overview. And again, there will be 2 more talks, right, in the next 2 days. One tomorrow at 9:30 at the Nano Institute at LMU, and another at Wednesday at 2 o'clock in the Max Planck Institute of Quantum Optics. So again, if you want to know more, especially more physics details, more physics-centered or sort of specialty-centered recent experiments, then please come then. So the floor is open for questions. So please raise your hand, and I will throw the cube to you, and I already see some of the guys over there. Okay, I'm supposed to throw, right? I should not walk, right? Oh, this is a good start.
Oh, oh. They supposedly throw that? Okay.
Good evening, Professor. Good evening, Professor. I'm a student studying electrical engineering at TUM, and naturally what concerns me really with these quantum mechanics structures is its applications in silicon. And one major problem that we're facing with high NA-EUV, which is TSMC is now putting in, is quantum tunneling. Now, I'm not very well versed in quantum mechanics, but how do you think you'll be able to, how can this be prevented? How can...
Good questions. I think usually electrical engineers that are working on the CMOS, quantum mechanics is their enemy rather than friends.
Yeah,
because of this,
true.
right? Basically, as you just kind of, the device becomes small, the gate dielectric is small, so this dielectric is supposedly a good insulator. There's no current should kind of flow through if you turn it off, but quantum tunneling will just kind of make the leakages through the switches, right? So that's kind of why that, since our old cell phones and computers still rely on the classical computing, basically heats up. So that is a serious issue, and and it's a very difficult to avoid because once you get down to such a small length scale, one of the nice thing about the quantum mechanics, nice thing or bad things about the quantum mechanics is basically even if you have the huge barriers, it can tunnel it through as long as it is thin. So this is inherent issues of the classical devices. So because of this is dictated by the quantum mechanics, the small length scale, there's no way that we can avoid that, right? So that's where that different type of the idea is needed. So can we make it kind of different way of the information processing, right? Can we make the different type of switches, right? So there are some of the ideas that, for example, there is an idea that people just try to use, can I just use a spin or spintronics type of the idea? Can I just use photons for this information processing? There are a few other ways that you can just use it. Or the really revolutionary idea is, can I just kind of not rely on the classical on-off type of the switching? Can I just use quantum qubits out of that, right? That is a revolutionary idea. Unfortunate part is no one yet just kind of come up with a way. Can I just kind of create this qubits, and can I just kind of replace all the quantum, the classical computing algorithm with the quantum algorithm? I don't think there has been yet the generalized quantum computing algorithm exists, so we don't know what this mapping should be, but at least in terms of the device point of view, unless you abandon this classical operation, basically really we are hitting the limits of the Moore's law because you get into atomic length scale, then we don't expect to see that classical computing, the data processing works anymore.
So, Professor, I'm sorry if may I ask another question?
Go ahead, yeah.
So I'm actually currently focusing on creating different geometries. So we use MOSFET and FinFET currently.
Yeah.
And so we are using different geometries to perhaps make it smaller. Do you think that will be a successful
It can delay a little bit. It can delay a little bit. I think there is a FinFET or even just idea that using semiconductor 2D materials, you can make the really thin bodies and you surround it with the gates. Yes, it works up to the certain limit, right? Maybe down to the 1 nanometer node, maybe work, right? With various things. But eventually, if you get down to 1 nanometer, now only, say, 10 atoms across it, right? Below that, no matter what you do, no matter what kind of materials you use, basically this classical field effect ranges idea should not work because of quantum tunneling, even at the room temperature.
The stock market is going to be very sorry after that.
Yeah.
Thank you, Professor, for your nice presentation. And actually, I'm a medical student, so I think for me it is kind of new knowledge for the physical world, quantum world. But luckily, you give us some very beautiful pictures to get us easy to understand. And for me, I have a question. commonly, I think I know the quantum or physics is more in mathematic way.
Yeah.
For example, like from 0, 1,
Yeah.
and there's some part in the shadow. So, but for me personally, I can't feel that. I don't know whether, so
Yeah.
I can't feel that,
Yeah.
and I can't think like the normal ways.
Yeah.
And I can't think the questions in that logic way. So my question is whether will there be one day this quantum thinking can be widely spread to like us common people,
Yeah.
and then at that time we can view the world in a very different way. Thank you.
That is very good question, and then really kind of crux of these things. Usually, the quantum mechanics we call is a kind of rather mysterious, and the first thing that we learn that quantum mechanics is so different from classical mechanics. I think, of course, also common thing is, quantum mechanics is so mysterious, or they're so difficult. No one can understand. Only a few people in the world that we understand. Even Einstein didn't understand all this kind of statement. I feel like that's already kind of misstated in the following way. Of course, there is some mysterious part that where our classical, the concept kind of dies off. But after 100 years, we've been seeing that kind of many of these things kind of arises. But it is true that the quantum mechanics, quantum object, is a rather feeble. Unless you have the really atomic scale, it's difficult to see the robust kind of magnification. It's out there. That's where that, in some sense, many of this, the quantum mechanical platform that I just introduced previously, is a way that you can at least kind of construct a macroscopic quantum object, quantum states, right? So superconductor is a good example. It is even in the macroscopic scale that you probably heard about this. Superconductors levitate on the top of the magnet. We can see, right, kind of unusual, why something is levitating. That is again dictated by the quantum mechanics. However, you can say that, well, this is a kind of low temperature effect, and you have to pour the liquid nitrogen. So one of the idea here is eventually, if you understand quantum mechanics better, and then also develop more of this material side, we may see that the superconductivity appears much higher temperature, maybe even room temperature. So that's his kind of future goal. Another thing that I want to mention is, in fact, quantum mechanics application is not necessarily kind of all remote, because you are medical students. I'm sure that you heard about this NMR imaging, right? If you go to the hospital, we are just going to the NMR imaging. Heart of the NMR imaging, or technology NMR imaging, rely on all the quantum mechanics. Of course, the nuclear magnetic resonance is a completely quantum mechanical effect that we need to understand to doing that. All this nucleon that we are dealing with, that is actually qubits that contains all the information. NMR is enabled by the very strong magnetic field that's supplied by the superconducting magnetic coil, right? So that's again another kind of important quantum mechanical effect. So in fact, quantum mechanical application is much closer than we think. That's kind of another comment I wish to make. Thanks for the very good questions, by the way.
Okay, so more raise hands, please. And you can throw, yeah. You need to throw them.
I'll do my best.
That was a football catch, sorry. So thank you for holding the very interesting lecture. I personally come from a computer science background, and I just came here for personal interest. But I have, first question is, as far as I understood, a qubit is between 0 and 1, whereas a traditional bit is always 0 or 1. First of all, what's the difference between the structure of a qubit and a bit? And second of all, what kind of influence could it have to large language models, databases, and I'm assuming that these kind of qubits can faster analyze algorithms. What do you think it's going to influence in those?
This is a kind of very good questions, and it's a kind of open questions as well. right? So as you said, that classical bit is a 0 and 1 and discrete, and quantum bit is basically kind of continuous because the superposition is allowed, right? And also quantum bits can be entangled with the many bits together, right? And then somehow the information is basically contains all kind of entangled states, which turns out that much larger so-called Hilbert space. In other words, information that we can coding into this entangled qubit is much larger, much larger. And the general idea behind of this one, I'm not an expert on this one, quantum algorithm, is basically because of this large Hilbert space and processing this one. In principle, that if you just kind of develop the right quantum algorithm dealing with the qubits, which is very different from classical algorithm, right? You can do a lot of this the computation, especially so-called NP-hard the problem, such as factorization, for example, big numbers factorization, which is an NP-hard problem, and that's why that we just use the old credit card securities basically using this two key, right? Those kind of things can be really efficiently computed using the quantum algorithm. Issue here is now, because it's a very different type of the algorithm you have to come up with. Not many people now yet figured out what type of problem can be solved, even if the quantum computers do exist now with a really kind of large capabilities. Right? We know that these are very different type of the machine and different type of these things work it out, but corresponding algorithm is yet just developed it out. So it turns out that many computer scientists as well as mathematicians, physicists worked really hard to come up with this kind of what, if you have this quantum computers now, we do have now at least kind of 10 qubits or 50 qubits, even 100 qubits, the quantum computer do exist, but what type of problem we can solve with this one? I think this becomes a really big issue. I'm not an expert on there, so you should probably, as a computer scientist, you will find out this is intriguing. One thing guarantee is basically it can be very different from classical algorithm and very different idea. Already the people are arguing that because of this, the massive information stored there and parallel the processing is possible, maybe this one might be very useful for some sort of optimizations or that kind of really parallel searching or search algorithm. So there are kind of few ideas leading it there. I don't know that what is really winning, and especially whether it's really possible that generalized the quantum computing algorithm can arise. But that's kind of interesting things to see. Yeah.
Thank you.
Martin, that is that was expert questions.
No,
Yeah.
it's more general than you think. So thank you very much for the nice talk. So I have a couple questions. One of them is the fact that you gave a really nice overview of the history of semiconductors and quantum. Are there any lessons that we can take from the past 70 years of semiconductors
Wow.
to take into quantum such that we can get this done faster?
Wow. Yeah. I'm not old enough to kind of live through that those 70 years. Probably half of that, a little bit more half of that. So I'm not sure that I can just kind of be kind of pretend a wise man here, right? But I think it's a kind of related following. I think that kind of let me spin that questions in following way. And many of you heard about the quantums and a lot of money is in there in the quantum, whether it's really getting it there or we are maybe foresee that so-called quantum interest. Oh, we put a lot of money in the quantum, nothing comes around, right? Type of things. But it's actually kind of interesting to see that how the semiconductor industry got evolved. Again, that I'm not a real expert, just reading through books and just kind of observing, right? When it started out, the transistor, right, 1950s, 45-ish, that's kind of transistor. That was really a centimeter object, right? Getting it there, the next breakthrough is probably transistors, kind of smaller, and becomes integrated circuits is around the 60s, right? And the VLSI and kind of things. So it takes a time, right? But then also you can ask that how much money actually they put in there. Nowadays, semiconductor industry, the development, putting the money is there, it's like the $1 trillion easily. Even within the companies that develop the next stages and putting the next stage of the factory lines, $1 trillion. And what is the end outcome is, in fact, if you just think about semiconductor devices, it's mind-boggling, right? You think that maybe this physicist working on the research can make the smallest things, right? Something really tiny things is completely wrong, right? We cannot beat the real engineers in the Samsungs and TSMCs, IMAX. There, that these semiconductor engineers can make 5 nanometers, 10 nanometer, and those kind of objects. Even with the best the device, the best e-beam lithography, whatever we just do, we cannot beat them. So not only they can make them, they can make billions of them, 10 billions of them in one chip, right? And the error rate is like 10 to the minus whatever number, 10 or something like this. It's such an engineering marvel, right? That can be done. And that is only few dollars even, right? So that is possible because over the time, over the half of the century, a lot of money is cut in there, right? Today we are hearing that, well, you know, quantum qubits that put the millions, tens of billions dollars, you get only 100 qubits. How on earth you can get there? How many years it takes? 5 years, 10 years, right? I think this is kind of giving us some lesson. It probably takes a long time, kind of longer time than we think, because it's not an easy problem, first of all. But also, learning from the semiconductor industry that if you just can put enough monies and the time, eventually it may actually work it out, right? Going back again that time, why the industry put this 10,000 kind of $1 trillion in that development? Because there's a markets, there's a things, there's a useful things comes around. So in a sense, it is not only scientific development, but it's coming with some applications and markets and those kind of things. So it's not only that we know that in principle it works and how it goes there, but how it can be used, what is kind of application based on what, and unless there is those kind of things comes in, the money will not come and we cannot make the next steps around. So I think that's kind of what is going to happen. Many of these things probably eventually going outside of the physicist hand. It's more of the engineering, it's more of the business side, but we'll see how and when this thing happen. So that's kind of something that I can put up there. Yeah.
Thank you very much. If I can, I would like to ask one more related question. It's regarding 2D materials, and it's now the 20th year since its discovery. Can we, do you ever see a scenario where the 2D materials are dominating the quantum devices, or they're being used in quantum devices?
I think in terms of the physics and science, I think we have still kind of some room to go, because I think there are many different types of 2D materials, many different combinations which has not been explored, right? Not to mention about different angles, right? However, in terms of the application and device applications, I think really kind of important hurdles that one has to go through the 2D materials. Is there a way that we can produce in the real scale of way? As a physicist, we're happy to deal with the kind of few devices, but to really convince the engineers to work on this in a more serious fashion, there should be some demonstration of the, is there a way the path is scaling up, right?
All right, thank you very much.
Yeah.
Okay. Oh, maybe the last couple of
Okay.
Yeah.
Well, first of all, thank you so much for the great lecture. And as you said, we couldn't really find a general algorithm that figures things out or solves the problems faster than classical computers.
That's right.
And like, this is the reason we couldn't really reach quantum supremacy. And do you think the reason for that is, do you think the problem is technological or scientific? Because, like, for example, non-locality,
Yeah.
the reason for entanglement, like,
Yeah.
as Einstein said, spooky action at a distance, we really don't know what that is and why is that happening. So do you think the problem is in our knowledge or in our technological advancements?
Yeah, okay, good. That's a very good question. I dare to say that in this case, Einstein is probably completely wrong. Because I think I would can rely on the authority of this Swedish Academy who just gave the Nobel Prize winners in the 2 years ago to basically decide kind of the quantum informations and the barrier inequality experimental proof. So out of 100 years of the efforts, I think there are numerous examples that indeed so-called the spooky action in the distance seems like the reality, experimentally measured quantities, right? So that's kind of the part. And that's, in some sense, one of the important the basis that all this kind of quantum technologies kind of rely on, right? So I think that was kind of well found, the fact, experimental fact that we can see now, not only just kind of theoretical propositions. However, where that kind of this limitation comes in, it's kind of still, I believe, is coming from both technological as well as our understanding, right? Our understanding is related with that. Is there a way that we can just make this one kind of more generalized? We can just kind of see that many of the example that indeed using this spooky action in the distance or the entanglement, demonstrating something kind of quite useful things going beyond that kind of few example we know about, right? So that's kind of going back to this quantum algorithm idea. To do that, we need kind of more of these qubits available and more longer time of operation. That's where the technological limitation. As I mentioned, to realize that some of the qubits work as a planned way, we have to make this error corrections to using the many other qubits. So although you can make the hundreds of qubits now, actually actual qubits that we can just make it functioning is the sum of the 10 qubits barely within the time because of all these error correction issues. So I think it is important to enhance those kind of the longer operation or the many qubit operation with a various way, including that my favorite subject of topologically protected qubits. And once you make the kind of many of the qubits working, when theorists, computer scientists, when play around, they may come up with a better idea, right? So I think that's kind of going together in some sense.
Okay.
Yeah.
Thank you.
Okay, last question.
Thank you. First of all, for the great lecture. My question will be maybe a bit general, but anyway, kind of related to the previous one. Thinking about the perspective of quantum sciences, what major or significant advancements should we expect in the nearest 2, 3, 5, 10 years? And maybe the follow-up, what prevents us from basically going forward? Is it budget problems? Is it our conceptual understanding issues?
I think right now, the budget-wise, worldwide, there are quite of the investments is happening. So I think budget-wise, there's kind of very strong development. How long this budget support will happen is again wait to see, because how long the people, government, or industries are patient enough just kind of to maintain this type of support or even expand that. That's kind of interesting questions to see, right? So I'm not an expert, and there may be some interesting things kind of figured out there. I think that there's quite healthy progress has been made in every aspect of the quantum science. So I just kind of today mentioned mostly quantum information processing, but there's another part, quantum communication, quantum sensing, and these are kind of another important part. And there has been also progress has been made and make the kind of more sensitive. Sensor is always important. Quantum communication becomes those kind of very important topics, especially a world like this that there's a kind of tensions goes up, and then you want kind of make the information process, the communication is kind of secure. So all this kind of things, there's kind of progress has been made and kind of in the really healthy way. But you may say that how long it will take? That's kind of really difficult questions to be asked, right? I'm certainly that progress is happening, that it was kind of slope is keep increasing. So, but I'm not sure that this is like the real exponential increase like what Moore's law is there, right? So how this curve should look like, it's very difficult to predict. But certainly, I think if I just project what was the status of the core like 10 years ago, it's a very different time, right? Because technologies got involved and that the new ideas kind of pops up. I'm pretty sure that with this project, in the next 10 years, with a very different type of the landscape in 10 years from now. What it will be, I don't know. I think that's kind of a good question. I wonder myself that how it will look like.
Thank you.
Okay, with this, let's thank Philip one more time.
Thank you very much. Yeah, thank you.